On November 7, 1940, the Tacoma Narrows bridge failed, not due to static pressure, but due to aeroelastic instability. Wind speeds of only 42 miles per hour induced self-excited oscillations known as torsional flutter. The bridge's slender plate girder deck lacked the necessary stiffness and aerodynamic profile to resist these dynamic forces. Torsional flutter involves the destructive coupling of aerodynamic forces with the structure's natural twisting mode. As the deck twisted, the angle of attack changed, amplifying the aerodynamic forces, which further increased the twisting motion. This positive feedback loop led to catastrophic failure within hours. The collapse fundamentally shifted civil engineering practice, establishing the necessity of dynamic wind analysis. Modern infrastructure design mandates that long-span bridges and high-rise structures must be analyzed for dynamic wind effects, moving far beyond simple static wind pressure calculations to ensure stability. Wind applies three fundamental forces to any structure: drag, lift, and the pitching moment. Drag acts parallel to the direction of the airflow, representing the resistance to motion. Lift acts perpendicular to the flow direction, often causing vertical displacement. The pitching moment is the rotational force acting around the deck's center of gravity. The magnitude of the drag force is calculated as half the air density multiplied by the drag coefficient, the reference area, and the square of the wind velocity. Lift force is determined using the analogous lift coefficient. The pitching moment coefficient quantifies the rotational stability or instability of the cross-section. These three coefficients are highly dependent on the structure's specific cross-sectional geometry and the angle of attack relative to the incoming wind flow. When wind flows past a non-streamlined structure, alternating vortices detach from the sides, forming the Kármán vortex street. This periodic detachment process, known as vortex shedding, generates oscillating lift forces perpendicular to the wind direction. If the frequency of this vortex shedding aligns precisely with the structure's natural frequency, resonance occurs. Resonance leads to a rapid buildup of vibrational energy and potentially large amplitude oscillations threatening structural integrity. The frequency of vortex shedding is calculated using the dimensionless Struhal number, which relates the wind velocity to the characteristic dimension of the structure. Engineers must design the bridge cross-section to ensure that the structure's natural frequency is sufficiently high or modify the geometry to disrupt the coherence of the vortex street, thereby avoiding destructive resonance. Aeroelastic instability describes the destructive coupling between aerodynamic forces and structural deformation. Galloping is a low-frequency, large-amplitude oscillation typically observed in non-circular cross-sections, such as iced cables or specific box girders. During galloping, structural motion alters the angle of attack, generating additional destabilizing lift forces that amplify the movement. Flutter is a high-frequency, self-excited vibration involving the simultaneous coupling of bending and torsional modes. Flutter is the most dangerous instability mode, occurring only above a specific critical wind speed. At this critical speed, the structure's effective aerodynamic damping becomes negative, causing the vibration amplitude to grow exponentially until failure. Modern bridge decks utilize passive mitigation techniques to stabilize airflow and reduce aerodynamic force coefficients. Streamlined box girders are employed to minimize flow separation and suppress vortex formation, significantly lowering both drag and lift coefficients. Incorporating central slots or open gratings within the deck disrupts the coherence of the vortex shedding pattern. These openings also equalize pressure differences between the top and bottom surfaces, reducing net lift. Fairings are aerodynamic extensions attached to the deck edges that smooth the airflow transition. Fairings effectively increase the critical wind speed required to initiate destructive flutter, providing an essential safety margin. These geometric modifications are fundamental for achieving inherent structural stability against dynamic wind loads. Structural damping systems dissipate vibrational energy, protecting the structure from excessive dynamic loads. Passive systems include tuned mass dampers or TMDs, which consist of large masses precisely tuned to match the structure's specific natural frequency. When the structure vibrates, the TMD oscillates out of phase, counteracting the resonant motion. Viscous dampers utilize fluid resistance to absorb kinetic energy, proving effective against both wind-induced and seismic loads. Active mass dampers, or AMDs, employ sensors and actuators to apply counterforces in real time based on measured structural response. AMDs offer superior performance in controlling multiple vibration modes simultaneously. However, AMDs require external power sources and complex control algorithms for reliable operation, increasing maintenance complexity compared to passive systems. Section model testing in specialized boundary layer wind tunnels is mandatory for verifying the aerodynamic performance of long-span bridges and tall buildings. These physical models accurately replicate the structure's geometry and critical dynamic properties, including mass distribution, stiffness ratios, and inherent damping characteristics. Testing determines the structure's critical flutter speed, ensuring it exceeds design requirements by a significant margin. Furthermore, testing verifies the aerodynamic coefficients and assesses serviceability limit states, such as pedestrian comfort under typical wind conditions. The results inform necessary design adjustments to the cross-section or damping systems. This rigorous process ensures the structure maintains safety margins defined by local building codes and international infrastructure standards, guaranteeing resilience against extreme wind events.